All right, so that means we have our first derivative, which is equal to, bring down our 6x to the 5th, minus, we bring down our 5, 20x to the 4th, and that disappears. Okay, so we want to know where that equals 0. (6x to the 5th minus 20x to the 4th equals 0. So actually, like I said, that's why it usually helps to factor it out, because if you factor it out, you have 2x to the 4th times 3x minus 10. So it's a little easier to find out where it equals 0 when it's already factored out. So instead of that, I'll just go ahead and write in the factored 2x to the 4th times 3x minus 10. Uh-oh, clean that up a little. Equals 0. There we go. All right, so we know if we separate both of those, x can either equal 0 or x can equal positive 10 over 3. So now we just find the second derivative at those points and see if it's positive or negative, and we'll know whether it's a maximum or minimum. At these points. Okay. So just like before, when you have that x equals 0, it's a pretty good chance that's going to be the point where it's inconclusive. Okay, oh, got to find our second derivative first. So your second derivative is equal to, might as well use it here, bring down our 5. We have 30x to the 4th minus, bring that down, 80x to the 3rd. And did I factor that one earlier? Nope, I didn't factor that one. Why didn't I do that? Could have sworn I factored that one. Oh, might as well factor it now. So we can pull a 10 out of both of those. So that would be x minus 8.
Would it be 3x?
Oh, 3x, thank you. Yep, 3x minus 8. Okay, so we just have to find at x equals 0, second derivative of 0 is equal to 0 times anything that's just going to equal 0. I'll write it out anyway. Okay, so once again, it's inconclusive. Use first derivative test. Okay. So since our other critical point is 10 over 3, we can still use negative 1 and 1. Okay, so let's see at f prime of negative 1. Remember, we're using our first derivative, or we can use that one, which would be a lot easier. That's 2 times negative 1 to the 4th times 2 times negative 1 minus 10. Okay, so we know here that's going to be positive because you have negative 1 to the 4th. And this is going to be negative because you have negative 2 minus 10. So you know that f prime of negative 1 is less than 0. Okay, so now we try it at 1. F prime of 1 is 2 times 1 to the 4th times 2 times 1 minus 10. Okay, so we know this is going to be positive, and this is going to be negative. Okay, so we know at f prime of 1, that's also less than 0. Okay, so you see when they have no actual change in direction, it's not a local minimum or maximum. So it's one of those things where the graph could be going negative, then hits that point where it hits 0, then it keeps going negative. So that's all it did here. It's going negative, then it went to 0 for that one moment at that one point, and then kept going down. Okay, so here there is no local, you can call them extrema, which is just branching together the minima and maxima. X equals 0 since the, let's say, f of x is decreasing on both sides. Let's clean that up a little bit. Okay, so we took care of x equals 0. That's neither local minimum or maximum. Now we need f double prime of 10 over 3. Create a little bit of a barrier. F double prime of, well, let me put my at 10 over 3. X equals 10 over 3. F double prime of 10 over 3. Where's my double prime? Here it is. Equals 10 times 10 over 3 to the third times 3 times 10 over 3 minus 8. Okay, so we can see here this is going to be positive. We don't even have to figure out what it is. And this, those cancel out, so you have 10 minus 8, so this is actually going to be positive. Okay, so we know that f double prime of 10 over 3 is greater than 0. So that means x equals 10 over 3 is a local minimum.
Wouldn't it be local maximum?
Nope, if it's greater than 0, it will be minimum.
If it was the first derivative, though, it would be the maximum.
Oh yeah, if it was the first derivative, if it's changing direction, it would be the maximum. I know, and that's the tricky part about this one. We have the local minimum and maximum. If the second derivative is positive, then it's the minimum. You would think it would be the other way around. Okay, but you think about it this way. So always kind of draw your graph and think about your slopes or your tangent lines. Okay, you notice your tangent line is increasing. So if it's increasing, then that will make where the slope is equal to 0 your minimum or your local minimum.
So I know the first derivative is the tangent line.
Mm-hmm.
What is the second derivative again?
The second derivative, because remember the second derivative is the acceleration function. So that's kind of the rate of change in your velocity. So if you can say your rate of change of your tangents are positive, then that means they're increasing. So it's kind of like if you're driving a car, that's pretty much like the standard example. If you're driving a car and you go from, let's say, if you're backing up 5 miles per hour, then you slowly start going forward, then that's where your second derivative would show your acceleration from where you started to where you're going.
If that's positive, then that's a local minimum?
Nope, because if it were, if it's positive, it's a local minimum. If it would have been negative, it would have been a maximum. Because right now your slope is going from negative, and as you're going to the right, your slope is increasing. So as long as the rate of change of your slope the rate of change of the rate of change is increasing or greater than 0, then you know that it's going to be a local minimum.
With the graph, I can picture that. That's fine.
Yeah.
It's when we don't have the graph and we're doing that,
Yeah.
is where
I know, trying to
that is
associate it together.
Yeah, you want to bring it back to the graph? That's, sure, no problem. I can understand that. But then you take the graph out.
I know, and just try to visual. And the thing is, with this, because it's such a crazy looking function, it's best not to try and visualize the actual function. That's why I keep it as low tech as I can. Exactly. So now, okay, if I want to know the difference between the local minimum and maximum using the second derivative, I keep it as that basic graph. Because these functions are going to get really complicated. All right. Any other questions on this one? All right. Okay, so now we're going to look at limits. Oh, is anybody else still writing? Oh, okay. We're going to look at limits at infinity. So now we've had limit as x approaches c, or x approaches 4, or -3, or whatever else. Now we're going to look at if limits just approach infinity. So as x just keeps getting bigger and bigger and bigger and never stops. Okay, so really, this section discusses end behavior. Of a function. On an infinite interval. Okay. So it's, say for example, just to kind of visualize it, let's say you have f of x equals 3x squared over x squared plus 1. Okay, so let's say from there, we draw our x and f of x. Okay, let's say we're starting at 0. X equals 0. Let's make this a little bit wider, just in case. Okay, so if x equals 0, you plug that in, you get 0. Okay, let's say if we're going this way, let's say we're increasing without bound. That means there's absolutely no limit to how high x can go. Okay, so let's say if we start off at 1. Okay, if we start off at 1, you end up with 1.5. Okay, let's say if you plug in 10, you actually end up with 2.97. And if you plug in 100, you end up with 2.9997. And it keeps on going. To where as you get closer and closer to infinity, this gets closer and closer to 3. So if you plugged in 1 billion, you'll get 2.999999999999997. So it just keeps getting closer and closer to 3. Okay, so let's say if we go in the opposite direction. Okay, so instead of increasing towards infinity, it's decreasing without bound. Okay, so what if we plugged in -1? The thing is, if you plugged in -1, they're both squares, so it'll become positive anyway, so it still ends up being 1.5. Same thing if you plugged in -10. It ends up being squared, so you still get 2.97. Same with -100. Get squared, and you end up with 2.9997. And it keeps on going. So as you get further and further towards negative infinity, oh, made that a little too big, ran out of room. Actually, let me get a little room there. There we go. So as you approach negative infinity, once again, your answer gets closer and closer to 3. Okay. So we know that the limit of 3x squared over x squared plus 1 as x approaches negative infinity is equal to 3. And the limit of 3x squared over x squared plus 1 as x approaches positive infinity is also equal to 3. Now, it won't always be the case where it's equal to 3 no matter which direction you go, but in this particular case it is. Okay, so if we were to graph this, okay, so we have our x and our y-axis. Okay, so this is our limit, which is equal to 3. Okay, so this graph actually looks like this. So I'll put it over here. So this is f of x equals 3x squared over x squared plus 1. Okay, so no matter how large you let x become, it'll never pass that. And no matter how small you let x become, it'll never pass that 3. Okay. Now this limit 3 is called a horizontal asymptote. Okay. So we'll give an actual definition of a horizontal asymptote. Okay, so the line y equals whatever your limit is a horizontal asymptote of f of x if the limit of f of x, oh, bring that up a little bit, as x approaches negative infinity equals L, or the limit of f of x as x approaches infinity equals L. And again, it doesn't have to be both. You may have a limit of 3 going towards infinity, and you may have a limit of 0 going towards negative infinity. So it could be different. Depends on the particular function. so we're about 20 minutes, we're good. Okay, so this is probably one of the most useful theorems in this particular section. So let's say if R, any number R is a positive rational number. And C is just any real number at all. Positive or negative. Then the limit of any constant over x to the r power as x approaches negative infinity equals 0, or the limit of any constant over x to the r as x approaches positive infinity equals 0. All right, so we'll do a quick example and kind of show the idea behind this one. Okay, so let's say, for example, we wanted to evaluate the limit of 5 minus 2 over x squared as x approaches infinity. Okay, so you have the limit 5 minus 2 over x squared as x approaches infinity. We can just go ahead and distribute that to both terms. So you have the limit of 5 as x approaches infinity minus the limit of 2 over x squared as x approaches infinity. Okay. So we know the limit of a constant is just a constant, so that stays as 5. But with the constant over any x squared, or x to the third or fourth or fifth or whatever it is, what they're saying is that if you have a constant, let's say 2, and x is just getting bigger and bigger. Let's say you have plug in 1, you have 2 over 1. If you plug in 10, you have 2 over 100. If you plug in bigger and bigger numbers, that numerator stays the same. So as that number on the bottom is getting bigger, you're getting closer and closer to 0. So if you have 2 over a billion, that's really close to 0. If you have 2 over a trillion, that's even closer. So as x is getting bigger and bigger and bigger, not only do you have x getting bigger, but you're now squaring it. So it's getting bigger even faster. So it's getting closer and closer and closer and closer to 0. So here, as the denominator increases, 2 over x squared approaches 0. Okay, so you have 5 minus 0, which is 5. Now, this is just going towards infinity. Towards negative infinity, it would be the same thing, because you have a number that's getting closer and closer and closer and closer to 0, but just on the other side of 0. All right, so any questions on that
So
one?
it's still equal 0?
Yep, just this term here.
Like, what I'm saying is if you're going negative infinity.
Oh, yep,
It would still equal.
Yep, it would still equal 0.
And if the constant at the top is -2, it'd still be the same one, right?
Oh yeah, if it's a constant, it doesn't matter at all. Oh, no problem. Okay, any other questions on this one? All right. Let's say for example, if we have to find the limit, let's say the limit of 2x to the third plus 5 over 3x squared plus 1 as x approaches infinity. Move that up a little bit. Okay. So we know if we did just plug in some really big number. Okay. So we know that just from our previous experience with limits. Let me just rewrite this real quick. This is actually equal to the limit of your numerator, 2x cubed plus 5 as x approaches infinity over the limit of 3x squared plus 1 as x approaches infinity. Okay. So here, if we actually did plug in some just really big numbers, you would end up with just infinity over infinity, because they'll just both keep growing nonstop. Okay. And once you get that infinity over infinity, it's called an indeterminate form. Just like 0 over 0 would be an indeterminate form. Okay. So once you hit that indeterminate form, you have to kind of manipulate the function a little bit. So here, whenever you have a fraction that comes out to be indeterminate, the quickest thing to do would be to divide it by the highest exponent in the denominator. By highest exponent, not exponent, highest variable and exponent. So for this one, you're going to divide everything by x squared. Okay, so you have the limit as x approaches infinity of 2x to the third divided by x squared plus 5 divided by x squared divided by 3x squared divided by x squared plus 1 divided by x squared. So you basically just multiply the numerator and denominator by 1 over x squared. Okay. So now if we did decide to, which you don't have to put the limit in both the numerator and denominator anymore, but if you wanted to, you could. You have the limit as x approaches infinity. You have 2x cubed over x squared, which gives you 2x. Plus, you have the limit of 5 over x squared, which stays 5 over x squared, over the limit as x approaches infinity. 3x squared over x squared is just 3, plus 1 over x squared. So we'll go ahead and put those just to join them together. Okay. So we know here the limit as this number, this actually just becomes 0. So we know that kind of disappears and becomes 0. But this one, no matter how big the number you get, you keep doubling it, it's just going to keep getting bigger and bigger. So here, we have infinity. But here, we know the limit of 1 over x squared is 0, so that disappears. But you have the limit of 3, which is just 3.